In this video, we're going to talk about what a scientific model is. We're going to go over different scientific models of the atom from about 400 BCE up until around early 1900s. The two newest models of the atom we're going to save from when we talk about electron configuration. That's what's called modern atomic theory. If you have your notebook and writing implement, let's go. So to start off with, when you think about what a model is basically just a scale replica, right? So for those of you who build like model cars or model rocket ships, whatever, it's just a miniaturized version of what you actually have in existence. A scientific model is very similar. It's a scale image. Usually in our cases, the scales are larger than what would be in normal life. And that scale model will tell us information about the structure, function, and relationships of all the different parts of that system. One thing to keep in mind is that these models are based on a lot of research and amounts of data. So we're not just pulling these things out of a hat. And another major point for science is if we discover new evidence that disagrees with the model that we have and we're able to confirm this new evidence, we change the model to take this into account, right? So we will change our model of something based on the information that we have at the time. This is not a bug, it's a feature. Right, so let's start off with some of the earliest models of the atom. And this will be early Greek, so around 400 BCE, Democritus. This isn't a scientific model in so much that there's no experimental evidence behind it, but it does get us to the point of having something called an atom, right? So let's say that you have some aluminum foil. What happens if you tear it in half? Right, now you have two pieces of aluminum foil that are smaller. If you take one of those pieces and you keep tearing it in half and tearing that half in half, and so on and so on and so on, what's eventually going to happen is that you're going to reach a point where you can't tear that atom or tear that sample in half anymore. When you get to that point, you have an atom. So atmos is the Greek word meaning indivisible, which is where we get the term atom from. Right? So this was a thought experiment in the 400s. Not scientific, but it gets us to the idea that there has to be a smallest particle that actually can exist. The first scientific model of the atom was around 1800, and this was from British naturalist John Dalton. Now, in his experimentation with different gases, what he was able to figure out was, well, first off, all elements are made up of small particles, right? And these particles are atoms. Atoms of a given element are identical to each other. So if I have 4 gold atoms, all 4 of those gold atoms are going to be the same. But an atom of gold is going to be different than an atom of silver. During normal chemical and physical processes, atoms can't be divided into anything smaller. And when you form compounds, atoms of elements can combine in special ratios to form that compound, right? So for example, in carbon monoxide, 1 atom of carbon combines with 1 atom of oxygen. In carbon dioxide, 1 atom of carbon combines with 2 atoms of oxygen. This is what's called the law of multiple proportions. Dalton theorized the atom to just be a solid sphere, what we would call the billiard ball model today, right? Billiard ball is just a solid sphere. Can't break it up. It doesn't interact with anything really except for when it does chemical reactions, but there are no charges, there are no smaller particles, nothing along those lines. It's just a sphere. Now we move forward about 100 years or so, and we get an experiment by J.J. Thomson. This is what's called the cathode ray experiment. A cathode ray tube is a tube that basically beams out negatively charged particles. For those of you who have ever seen like those old, really thick TVs or computer monitors, those are CRTs, cathode ray tubes. So they work on this principle, right? And the idea is, again, you fire out these negatively charged particles. Charged particles are bent by magnetic fields. Now, since the particles are negatively charged, they're going to be bent towards the positive plate, right? The positive magnetic field. This happens regardless of the metal that you use to create that cathode ray, right? So if you use steel or aluminum or copper or silver, whatever, this all happens. So what Thomson was able to take from this was the idea that all elements have these tiny little negatively charged particles in them that wound up being called electrons. And this brings us into his model of the atom, which is called the plum pudding model, plum pudding being a British dessert. The idea is that you have this overall positively charged stuff, for lack of a better phrase, and inside that positively charged stuff, you have enough electrons to balance out the positive charge. The reason being, atoms are still electrically neutral overall, so we have to make sure the positive equals the negative. All we did here, something to notice, we took the billiard ball model, which was our current working model of the atom. We found evidence that, hey, we can actually break this up into some smaller particles like our electrons. So we took our billiard ball model and changed it to account for the presence of electrons. Right? So again, when evidence comes out, our model changes. If we come forward about another 8 or so years, we get to the work of Ernst Rutherford. Now, one thing to keep in mind in science is that experiments are generally designed to try to disprove assertions. So, in order to try to disprove Thomson's assertion that electrons existed, what Rutherford wound up doing was he took an alpha particle generator. Alpha particles are radioactive particles. They're basically the nucleus of helium atoms. They didn't know that at the time, though. And he fired it at a sheet of gold foil. The reason why he chose gold was because gold was extremely dense, right? So there should be a lot of matter in a very small area. Now, if Thomson's model were correct, what should happen is that the alpha particles being fired at high speed should rip right through the gold, right through that positively charged stuff, and come out the atom on the other side without any deflection. He ran the experiment, and as we can see in the diagram here, most of the particles did go through with very minimal to no deflection. But a couple of particles bounced off at fairly large angles, and a few particles actually bounced straight back. How can you have a particle bounce straight back on a piece of gold foil if the atom is just positively charged stuff? Well, his explanation for this is if we have something that can deflect a positively charged alpha particle, that something has to be positively charged. Now, again, the stuff that the atom was thought to be made of was positively charged. But since only a very small amount of atoms showed any deflection, the positively charged stuff that alpha particle struck off of had to be extremely small. And since most of the particles passed through with zero deflection, then that means that the remaining portion of the atom has to essentially be empty space. Right? So this was the discovery of the nucleus, that small positive region in the center of an atom. And then electrons just orbited around the nucleus like planets around the sun, because again, that made sense, right? Again, all we did here is we took the plum pudding model, which said you had these negatively charged electrons floating inside this positively charged stuff. We figure out that positively charged stuff isn't actually that large. It's actually really small. So we shrink that positively charged stuff down to form a nucleus. And we still have all these electrons lying around. So we're just going to have them orbit the nucleus. Right? So experimental evidence took us from billiard ball model to plum pudding model to the nuclear model. When we get into the electron configuration portion of this, we're going to learn about the Bohr model, which is the solar system model you guys used last year. and then the electron cloud model or quantum mechanical model, which is our current working model of the atom. So that's it for this video. I will see you guys in class.